With these extra questions for topic C that I missed out. 26. A simple pendulum undergoes simple harmonic motion. GPE of the pendulum is 0 at the equilibrium position. How many times during one oscillation is kinetic energy of the pendulum equal to its gravitational potential energy? So what we have is our simple pendulum. Let's make it E log. It is moving from up here to here, right? And this is the movement, and our GPE is 0 here. So we're defining this as H is equal to 0. This point. And so GPE is equal to 0. And now that means our KE is max. It's at its maximum, right? And the total energy, E total, is equal to PE, sorry, energy potential plus energy kinetic, right? Which is constant. Our total should be constant. So that means when we have, let's look at the path of this pendulum. Let's say it starts here, then it goes up here, right? Then it comes back down, and goes up, and comes back here. And that's one full oscillation, right? Now, how many times? So we want our GPE to equal our KE, or let's just say E potential, just because I wrote it that way. So EK, and so somewhere in the middle, right? Or we'll get this situation, right? Somewhere when we're here, some of that KE is converted into GPE, and it should be about the same. Then when we're coming back down, again, we have same GPE and KE. And here again, our GPE is 0, then it becomes equal to our kinetic energy. Then our kinetic energy is 0 here, right, at this line, because it's about to return back. And then we have, again, this situation. So we see it 4 times. 4 times. And so our answer is D. Now, when monochromatic light is incident on a single slit, a diffraction pattern forms on a screen. The width of the slit is decreased. Okay. What are the changes in the width and the intensity of the central max of the diffraction pattern? And so we have our formula, right? Theta, which is angle between angle to first minima, right? Right, and what is that equal to? Lambda over b, and this is our slit width. And so if our width increases, yeah. If our width decreases, our theta increases. And so the width of our central maximum, which is related directly to theta, increases. And the next thing is intensity of central maximum. So that's not related to anything else except the fact that, or if we have a smaller width, let's say we have this, more light is gonna pass through, right? Now, if we close the slit, we have less light passing through. So B decreases, intensity of central maxima, intensity of central maxima decreases, because we have less light, and intensity is equal to the power per area, right? And less light just means less power and less area. So less photons per unit area. So our central maximum intensity decreases, and we have B. And on to 28. We have monochromatic light of wavelength lambda in air is incident normally on a thin liquid film of refractive index m is suspended in air. The rays are shown at an angle to the normal for clarity. Angle to the normal for clarity. Okay. What is the minimum thickness of the film so that the reflected light undergoes constructive interference? Constructive interference. So this is thin film interference, right? And this is actually the old syllabus. Let me just... So I'm not sure if this would come up. I don't think so, but we can still solve it. This is... So we have a formula where, say, for thin film interference, where we have this, and m is actually what we have n as in our data booklet now, and this is our refractive index, right? And this is constructive interference. That means we have to use the formula for destructive interference. And so typically this is the formula for destructive, right? But when we have a reflection, we have, when we're going from air to a more dense, less dense to more dense material, reflection from less dense to more dense material with light specifically, then we have, therefore, a phase change, a 180-degree or pi phase change, right? And so that causes us to now use the reversed formula. And so this is for constructive interference, and what we would have is minimum thickness. This is our thickness, d. So d is equal to m plus half lambda over 2n. And if we want to find the minimum, we just put in 0, and we get lambda over 4n, and that is there. Our answer is A. Now let's move on to this. A beam of light containing two different wavelengths is incident on a diffraction gradient. The wavelengths are just resolved in the third order of diffraction. What change increases the resolution of the image? Increases the resolution of the image. Now, this is old syllabus as well, resolution, and we have a formula for that, but we do not need to do this, so let's avoid this question. Then we have, okay, it seems like that is it. We only had those few questions, and hopefully you guys learned a bit more. This was the extra questions for topic C, and that's it for now. Thank you guys. Please drop a like and subscribe if it did help.